Hello and welcome to part 3 of the book summary and review series, where we'll be going through chapter 4 to learn more about the blue pill pin's capabilities and the simple LED code that goes with it. Here are the key ideas in this chapter. Like the Arduinos, the pins could be configured as input or output pins, and some of them are specialized to do certain functions such as SPI or I2C communication. A GPIO port is a group of pins, and there are 3 ports named GPIO A, B, C in the blue pill. How to set them up with libOpenCM3, which we'll look into later. And finally, the issue with program delays. First, let's talk more about the input pin configurations in the blue pill. There isn't anything too special here. It's your typical input pin configs. Analog input and digital input. There's the option with digital input pull up and pull down, which means that your input is always either high or low with no floating noise at all. Next, we have the output pins. Now for the output pins, we have slightly more configuration needed. Push-pull, which is your typical digital output pins, and the macro alternate FN, which is to specify that the pins are going to be used for special functions such as SPI or I2C communication. It's also possible to configure the pin as open drain configuration, which means that it could only be outputting ground or floating. When the pin is in open drain configuration, it essentially becomes an NMOS transistor. Let's take a closer look on this configuration. So, here's a simplified circuit diagram when the pin is in open drain mode. This is the NMOS transistor connected to the pin. So let's imagine that the V in here is set to high initially. This causes the transistor circuit to be switched on and the V out to be shorted to the ground. The output of the pin will then be grounded. Now, let's switch off the transistor and notice that now the pin is disconnected from the ground and it is essentially floating as it's disconnected. So this pin output could only be either ground or floating, and this configuration is called open drain. It is used in certain situations such as I2C communication, where the pins are pulling the data and clock wires from high to ground. Moving on, let's examine the code given. First, in the setup function, the RCC Peripheral Enable function is called. This is to ensure that the clock on the port is activated and that we are able to control the pins, such as toggling it. Then, we set the mode of the pin with the GPIO Set Mode function. It takes in 4 arguments: the GPIO port, the GPIO input or output mode with speed, the configuration of the pin, and finally, the pin number. The book covers the definitions of the function arguments very well, and it even provides 4 tables to go along with it. And finally, there's the block of code that's responsible for program delays. It's rather straightforward, but do take note of the reverse configuration, where the clear function causes the LED to switch on rather than switch off. This is due to the way that the board is wired. Also, the for loop contains the code ASMNOP, which is an assembly function that does nothing. This is done explicitly so that the for loop is not skipped due to compiler optimization. Other than that, it's pretty much your typical blink LED code with program delays in it. Which brings us to our final point in this chapter, program delays. While they are easy to code, they could be problematic when dealing with multitasking, such as trying to blink 2 LED lights at different rates. This is where the next chapter comes in and talk about the free RTOS library, where it offers programming APIs that standardizes and allow multitasking easily. And with that in mind, I would like to end this video. Thank you for watching and keep on learning.